Hello students, in last session we learned about rotational kinematics and then started a new topic, that is torque. In the present session I will first explain some questions based on torque and then will introduce two more subtopics, that is principle of moments and center of gravity. I hope you are enjoying the sessions. So let's get started.
See, already we had learnt about the torque, what it is and how it is mathematically calculated. So, first I will start with the example of calculation of torque and then we'll proceed further. In this example, a force is given there. This is the vector representation of force, that is equal to I minus 2j plus 3k, and position vector is given as well, that is 3i plus 2j plus k. So force and position vector both are provided. It is asking for torque acting on the particle about origin. Now here this has to be about origin. So directly we can write torque as R cross F. Otherwise, if any reference point had given, then we had to write position vector with respect to that reference point. But this time, since the reference point is origin itself, so directly we can write position vector as 3i plus 2j plus k and calculate it like it is written. So that will be 3i plus 2j plus k cross I minus 2j plus 3k. You must be knowing how to calculate the cross product. So let us see. Write this I, j and k. I am using the matrix method. Here it will be 3, 2, 1, and in next row this is 1, minus 2 and 3. On solving this, we will get 6 plus 2i minus 9 minus 1j plus minus 6 minus 2k, that is equal to 8i minus 8j minus 8k. This is the torque which is asked here in the question. One more example is there to illustrate how torque is calculated for a physical situation. This time it is given the example of a projectile. A particle of mass m has been thrown up with initial speed u, making angle theta with horizontal. Find the torque of its weight about the point of projection when it just reached the highest point. Okay, let us first draw the situation. It has come to its highest point, this being angle of projection. This is initial speed u. It is asking torque of gravity about the point of projection, but it has to be the weight at this point, that is equal to mg here. This is the position vector of the particle at the short moment, let that be r. So here we have to again write torque about projection point. I have written O as projection point, that has to be equal to r cross mg. Now this r will be having two components, one along the x direction and other along the y direction. And as we know that there is need of only x direction component because it is the perpendicular distance from projection point to the point of application of force. So this will be reduced to, if we are interested only in its magnitude, it will be reduced to, let us write this point A, that will be OA multiplied with mg. And what is this OA? It has to be half of the horizontal range, and horizontal range as you know is u square sine 2 theta upon g, but half of this, so upon 2g multiplied with mg. These two got cancelled and then we got mu square sine 2 theta upon 2. This is the torque about point of projection when the particle has reached at its highest point, and it is torque of weight of the particle, which can be written as, because we know sine 2 theta can be written as 2 sine theta cos theta, so it can be further simplified to mu square sine theta into cos theta. This is the value of torque. Consider a pulley fixed at its center of mass by a clamp. A light rope is wound over it and the free end is tied to a block. The tension in rope is T. Write the forces acting on the pulley and how are they related. Second, locate the axis of rotation and find torque of forces about the axis of rotation. Here this block is having mass m. First consider the pulley. What forces will be there on the pulley? Its weight, that has to be in downward direction. Tension by the rope, it has to be like this. And then contact force by the support at center. Now, in which direction this normal has to be? Because tension and mg both are acting in downward direction. So, of course, normal has to be in upward direction. And then we can write N to be equal to T plus mg. Since center of mass of pulley is at rest, so we have to write net force to be 0 for the pulley. Now, axis of rotation has to be the line through the center of pulley. So, it has to be, for part B, these were the forces. So, part A is simply normal, tension and mg, and this is the relation given here. For part B, we have to write the axis of rotation. So, it has to be through the center of pulley and in direction perpendicular to this plane. So, it has to be center of pulley and perpendicular to its plane. These are very basic concepts of torque. The third one is find the torque of forces about the axis of rotation. Now, as normal and weight are passing through center of mass itself, that is center of pulley, so there will be no torque effective for N and mg about rotation axis. The only torque effective will be due to tension, and let this distance be equal to r. Then we can write the only torque effective to be equal to T multiplied with r. That has to be torque about the axis of rotation, where axis of rotation is passing through center of pulley. Now I am going to consider one more subtopic, that is equilibrium of a rigid body. If you can recall, we had discussed equilibrium of a point in our chapter laws of motion, because that time for a point only translation motion has to be associated. Here for equilibrium of rigid body, it is not only translation, we have to check for conditions of rotation as well. So if a rigid body is in equilibrium, it must satisfy both the conditions. First condition is that net force has to be 0 and the second, net torque has to be 0. So we have to write both the equations here, equilibrium of force and equilibrium of torque. In other words, we can say that a rigid body is said to be mechanical equilibrium if its linear momentum as well as angular momentum are not changing with time. Because if force is not acting, linear momentum conservation can be written, and in the same manner when torque is not acting, we can write conservation of angular momentum. So this is the conditions to be written for equilibrium of a rigid body, that will be summation of Fi to be 0 and then summation of torque to be 0, and this will lead to the condition linear momentum is constant, also angular momentum is constant. Angular momentum we haven't used earlier, it can be written in the same manner as we relate force and linear momentum. So here this torque can be written as dl by dt, and if torque is 0, of course dl by dt will be 0. So we can write angular momentum to be conserved, that is constant. Before and after event it will be having the same value. Now let us see how the equations are solved on this concept, that is equilibrium of a rigid body. One example is here. If the mechanical advantage of a lever is 100 when a force of 10 Newton acts at a distance of 20 cm from the point of fulcrum, calculate the force acting on the other side of the fulcrum and the distance of that force from the fulcrum. Now here mechanical advantage, you must have learnt about this in your junior classes, that is equal to d2 upon d1, and it has to be equal to F1 upon F2. It is nothing but the principle of moment, and from principle of moment it can be written F1 d1 should be equal to F2 d2 about the hinge. So here it will be d2 by d1 is equal to F1 by F2, and mechanical advantage is given here, that is 100. So 100 is equal to 10 upon F2. By this we will get value of F2, which is equal to 10 upon 100, that is 1 by 10 Newton. Also, since d2 by d1 is mechanical advantage as well, so we can write d2 to be equal to mechanical advantage into d1, and d1 is given 20 centimeter, so this will be equal to 100 into 20, that is 2000 centimeter, which is equal to 20 meter. So in this question we have used principle of moment with the help of a simple lever. The next thing that we have to learn about is center of gravity. Now what is meaning of this term center of gravity? We all are now familiar with the term center of mass. So it is almost like that center of mass only, but here the center of gravity is a point where we have to assume whole weight of the body to be concentrated. Now if you can recall, in center of mass we had said that it is the point where whole mass of the body has to be concentrated, and here it is the whole weight. So we can define it like it is a point where if we consider whole the weight of body to be concentrated, then the same acceleration will be for the point as it is for the whole body under the application of same force. So everything is identical except that this time mass has to be replaced by weight, and of course mathematically also it will be having a similar kind of definition. So we can write R of center of gravity as, again this has to be for both kinds of system, that is for discrete mass system and for continuous mass system. So first I am defining it for discrete mass system. This one is for discrete mass system. Now you all know what is discrete mass system. It is a system in which the mass is distributed randomly at different points. So for this kind of system we can write RCG to be equal to summation of, it should be in place of mass, now we have to write the weight. So it has to be MIGI RI upon summation MIGI. Now this will lead to a very interesting result. See, here it is written summation of MIGI. What does it mean? Because this term has come as an additional term, so GI is acceleration due to gravity at different points of the body. Should it be same for all the points? If it is same, then of course we can take it outside, because if it is constant we can take it outside and then can write this to be equal to summation of MIRI. In denominator also G, if it can be taken outside, this will be summation of MI, and now this term, because these two got cancelled, will be equal to RCM. From here now we can conclude that if G is constant all over the body, then of course center of gravity will be having the same location as the center of mass. But what if the body is very large, if it is very huge like a big mountain or a glacier or an ocean? For those bodies, for very large bodies, we cannot take G to be constant all over the body, and then for those bodies RCG cannot be equal to RCM. But for our general everyday use objects like for a car, for a pen, for a pencil, for our board, for even ourselves, we can of course write RCM to be equal to RCG. So you have to be very careful about using the word RCG and CM. It will be same for all general sized bodies, but for very large bodies these two terms are different. Then we have to consider where the effective weight is acting on the point, that will be center of gravity. Let us solve one example as it is given here. Figures 1 and 2 below show a metal stick, half of which is wood and half of which is steel. As we know, steel is denser than wood. In figure 1, the stick is pivoted at the wooden end at O and a force F is applied to the steel end. You can see here in diagram it is shown. In figure 2, the stick is pivoted at the steel end at O and identical force is applied to the wooden end. Here we have to neglect weight of the rods because gravity is to be neglected. Then it is asking for what will be the angular acceleration in which rod it will be having greater value. So let us see the example. In first example, in figure 1, the force is acting at steel part and it is pivoted at O, which is on the wood part. If we check for the torque, then torque will be having the same value because in both the rods forces are same and there is perpendicular distance with the point about which it is to be rotated is also the same. So torque has to be equal for both the rods. Torques are equal, and from the relation torque is equal to I alpha, we have to compare alpha. So let us compare moment of inertia now. Here point of rotation is O, so we have to check what is moment of inertia about O. So for figure 1, moment of inertia will be having more value about O as compared to the figure 2 because steel is having more density, so heavier mass is at the farther end in figure 1, and angular momentum if it is and moment of inertia if it is more, then from the relation torque is equal to I alpha, alpha has to be small. So now we can say that in figure 1, angular acceleration will be smaller than as compared to figure 2. And then our correct option is option number C, in which it is saying that in second, angular acceleration is greater than in first. Now I have taken one example here from center of gravity. A metal rod of length 50 cm having mass 2 kg is supported on two edges placed 10 cm from each end. Let us draw this situation. The whole length is given 50 cm and its mass is 2 kg. Of course, its weight has to be at the middle because it is a uniform metallic rod. So this will be 2g at the center of rod, where its center of gravity as well as center of mass is lying. Now these two edges on which it is placed are 10 cm from each end. So let this be the position of edges for each. This distance is equal to 10 cm. A 3 kg load is suspended at 20 cm from one end. Let us just consider from any end. Let this be the position of another mass that is hanging from here. It should be equal to 3g. The weight for that body I have written. Find the reactions at the edges. Okay. Now again we have to apply principle of moments. So let us consider that these reactions are equal to N1 and N2. Now as you all know, if it would have been a symmetric condition, then we would have written these two normals to be equal. But since an external weight is applied on one side, so we cannot write N1 to be equal to N2. Now we have to apply the principle of moments. Let us first locate the points. So if this be E, end be A, this point be D, this is center C, other end B, and this one the other edge F. We can write now R1 plus R2 minus 3g minus 2g is equal to 0. What is this condition? This is equilibrium of a rigid body and I have written net force to be equal to 0. From here we will get R1 plus R2 is equal to 50 Newton. Now since this is a rigid body, so we have to apply other condition as well, that is net torque also should be equal to 0. So if you write now torque of all the forces, then first you have to consider that about which point you will write the torque. So it is always beneficial if you write torque about a point at which any of the force is acting, because then for that force torque will be 0 about that particular point. So it will be very easy if we write for the point at which N2 is acting, that is the point F. Now I am writing net torque about F to be 0. You have to now check for the directions of torque. If you can see, 2G and 3G both will try to rotate the rod in anti-clockwise direction, whereas this N1 will try to rotate in clockwise direction. So simply balance these two torques. I am writing clockwise torque to be equal to anti-clockwise torque. About the point F I am writing. So now I am writing the equation torque about F to be 0. Let us see. First consider the clockwise torque, that will be equal to N1 into. Now what is distance of N1 from this point F? It has to be 50 minus 20. So that is 30. N1 into 30. This has to be equal to net anti-clockwise torque, and these torques are 20 for 2G I am writing. So it is 20. This distance FC will be equal to 15 plus 30 into this time this 3G is at a distance 20 centimeter from one of the end. So it will be at a distance 20 centimeter from F as well. So that will be 20. Now if we solve, N1 into 30 will be equal to 300 plus 600 equal to 900, and N1 we got as 900 upon 30, that is equal to 30 Newton. So once we got value of N1, now with the help of this equation R1 plus R2 we can get value of N2 as well. This R1 and R2 are the same as N1 and N2. This is N1, this one is N2. So we can write N2 to be equal to, from here it will be 20 Newton, which is the reactions at the edges. One is 30 Newton and other is 20 Newton. With this, our today's session is complete. We have discussed today equilibrium of a rigid body, how the conditions are different from equilibrium of a particle, and then we saw principle of moments and center of gravity as well. Now I hope you will be comfortable with numericals if it is related to equilibrium of a rigid body or location of center of gravity, or even if it is from a simple lever. We had discussed one question also, that was from the mechanical advantage of a simple lever. So that concept also is introduced. You must have studied about it in your junior classes, and now it is discussed again here, because sometimes, especially in NEET, you may get a question that is from the mechanical advantage. So with this, now I think you will be able to solve the questions related to that portion also. The different terminology that is used for lever has to be remembered. The lever is a system that works in mechanical equilibrium. It is like a seesaw on the children's playground, and that also is a typical example of a lever. So an ideal lever, always it essentially has to be light. We generally do not write weight of the lever, and the rod is pivoted at a point. That point is known as fulcrum. So with the word fulcrum, it must strike in your mind that this is the point of hinge. In coming sessions, we will do some more questions based on these all topics, and then we'll collectively solve the questions related to all the topics from rotation and center of mass. Till then, practicing more and more number of numericals. In the next topic, I will start teaching about a new concept that is known as moment of inertia, and you will see how this is used in case of rotation as we use mass in case of translation. So this is simply a replacement of mass in case of rotation. Now with learning of all these topics, you must have understood that all the concepts we were applying in translation can be applied here also in rotation. Only some terms have to be replaced, like we had replaced force with torque. linear momentum with angular momentum, and now it will be mass with the moment of inertia. So let us look forward to the next session where we will discuss everything about moment of inertia. Till then, goodbye.